In the quiet town of Oxford, nestled among rolling hills and ivy-covered walls, there is a tale that has puzzled scientists for over a century. It's not just any old story but one that challenges our very understanding of reality itself: quantum entanglement. Imagine this: two particles separated by vast distances can somehow communicate with each other instantly, as if they're in the same room. This phenomenon was first observed back in 1935 by a brilliant physicist named Albert Einstein and his colleagues Boris Podolsky and Nathan Rosen. They called it spooky action at a distance. Einstein had a hard time accepting this idea because he believed that information couldn't travel faster than light, which is the cosmic speed limit set down by none other than himself in his famous theory of relativity. But what if Einstein was wrong? What if these particles were not just communicating, but actually sharing a deep, mysterious connection that transcends space and time? Let's take you back to 1935. Einstein, Podolsky, and Rosen published their paper, questioning the completeness of quantum mechanics. They proposed an idea called hidden variables, suggesting there might be some undiscovered mechanism explaining this spooky action. However, another physicist named Erwin Schrödinger entered the fray with a different perspective. He argued that it wasn't about hidden variables but rather how we interpret these particles and their relationships to each other. This back and forth between Einstein's skepticism and Schrödinger's curiosity laid the groundwork for what would become one of science's most intriguing puzzles. Now, fast forward nearly 90 years later, scientists are still exploring this strange case. Today, quantum entanglement is not just a theoretical concept, it has practical applications in fields like cryptography, computing, and even teleportation experiments. In recent years, researchers have conducted tests that seem to confirm the existence of these connections across distances. They've performed experiments using photons, electrons, and other particles in the heart of a bustling city. Under the neon lights that flicker like stars in the night sky stands an old library. The building hums with the whispers of countless tales waiting to be uncovered. Tonight, I find myself drawn into one such tale, a story that has puzzled scientists for decades and continues to challenge our understanding of reality itself: quantum entanglement. Quantum mechanics is a field where logic often seems to take a back seat to sheer bewilderment. It's a realm so strange and counterintuitive that even Albert Einstein, the mastermind behind general relativity, famously dismissed it as spooky action at a distance. Yet here we are, decades later, still grappling with these concepts. Quantum entanglement is one of those enigmatic phenomena that defies common sense. Imagine two particles so intimately connected that no matter how far apart they are in the universe, changes to their properties instantaneously affect each other. This concept was first proposed by physicist Erwin Schrödinger and has since been a cornerstone of quantum mechanics. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published a paper that introduced what is now known as the EPR paradox. They argued that if quantum entanglement were real, it would imply something called non-locality, meaning information could be transmitted faster than light. This was against the rules of relativity, which state nothing can travel faster than the speed of light. Einstein's skepticism stemmed from his belief in local hidden variables, a concept suggesting there must be some underlying mechanism that causes entangled particles to behave as they do, even if we don't understand it yet. He famously referred to this idea as a spooky action at a distance, using the word spooky because of its eerie and seemingly magical implications. However, over time, experiments began to challenge Einstein's notion. In 1964, physicist John Stuart Bell proposed a test that could determine in the heart of our universe lies a mystery so strange that it defies both logic and intuition. Imagine if you could send a message to your friend instantly, no matter how far apart you were, no time for light or sound to carry those words between you. This is not just science fiction, this is real. It's the phenomenon known as quantum entanglement. Quantum mechanics, often seen as an abstract and complex field of study, has thrown us a curveball with its predictions that particles can be connected in such a way that their states depend on each other regardless of distance. Albert Einstein famously called it spooky action at a distance, but the reality is far more fascinating than any mere description. Consider two entangled particles, let's call them particle A and particle B. If we measure something about particle A, say, its spin or polarization in one direction, we will instantaneously know that particle B has flipped to match it. This happens even if they are light years apart, no signal travels between them, their states simply remain connected. This concept challenges our everyday understanding of the world. In classical physics, a change here should not immediately affect something far away without some kind of intermediary force or wave. But quantum mechanics tells us that these connections can exist and operate in ways we cannot fully comprehend yet. The story begins with experiments conducted by physicists like John Bell in the 1960s. He devised tests to see if entanglement was just a mathematical curiosity or something real. His famous inequality, now known as Bell's theorem, showed that local hidden variable theories could not explain certain experimental outcomes without invoking non-local effects. Over time, experiments have only strengthened our belief in the reality of quantum entanglement. In 2015, the Chinese MISHA satellite achieved this effect over vast distances on Earth, proving it works even at scales beyond what was previously tested. Yet, despite all these advancements and evidence, many physicists are still grappling. The night was clear, and the stars twinkled in a silent dance above. In this serene setting of quiet contemplation, I find myself pondering one of science's most bizarre phenomena, quantum entanglement. It's a tale that intertwines logic with mystery, defying our everyday experiences yet holding the key to unlocking profound secrets about reality itself. Quantum mechanics is often described as an odd and counterintuitive realm where particles can instantaneously affect each other regardless of distance, a phenomenon Albert Einstein famously called spooky action at a distance. This concept challenges everything we hold dear about cause and effect, challenging our very notion of space and time. Let's step back to the early 20th century when quantum mechanics was born out of necessity. Physicists were grappling with inconsistencies in classical physics that couldn't explain certain behaviors observed on atomic scales. Enter Max Planck, who introduced quantization of energy, a concept that would change everything. Then came Niels Bohr and his model of the atom, which proposed electrons orbiting the nucleus in discrete orbits. This was a radical departure from the smooth trajectories we observe in macroscopic objects like planets or cars. Yet it worked incredibly well for explaining atomic spectra. But as physicist Werner Heisenberg developed matrix mechanics alongside Erwin Schrödinger's wave equation, they began to see that particles could exist not just at one point but in multiple states simultaneously until measured, an idea encapsulated by the famous cat thought experiment proposed by Niels Bohr and Werner Heisenberg's collaborator, John von Neumann. This concept of superposition is mind-bending. A particle can be here or there, up or down, spinning clockwise or counterclockwise, until it's observed. In 1935, Einstein, Boris Podolsky, and Nathan Rosen published their famous paper suggesting that quantum mechanics was incomplete because the theory failed to describe hidden variables. This meant particles could influence each other instantaneously over vast distances in the realm where photons dance in pairs, their properties mysteriously mirroring each other even when separated by vast distances. We find a phenomenon that challenges our very understanding of reality. Quantum entanglement, a concept so bizarre it seems to defy logic, has profound implications for how we perceive the world around us. Firstly, let's consider the impact on technology and communication. Imagine if information could be transmitted instantly between 2 points without any physical medium or loss in speed. This is not just a theoretical dream. Experiments have shown that particles entangled over distances of hundreds of kilometers can indeed communicate their states with astonishing precision. The potential for secure quantum cryptography, where messages are encoded using the principles of entanglement to prevent eavesdropping and ensure absolute privacy, opens up new possibilities in data security. But beyond mere communication lies a world of untapped computational power. Quantum computers harness the properties of entangled particles to perform complex calculations at speeds unattainable by classical machines. The implications are vast, from cracking encryption codes that currently protect our most sensitive information, to simulating molecular structures for developing new drugs and materials with unprecedented precision. However, as with any revolutionary technology, there is a darker side. The same principles that make quantum entanglement so powerful could also be used in ways we might not want. For instance, the ability to transmit information instantaneously raises ethical questions about privacy and surveillance. If governments or corporations could monitor communications without consent, the balance of power would shift dramatically. Moreover, as scientists continue to explore the boundaries of this phenomenon, they uncover philosophical implications that challenge our understanding of free will and determinism. The idea that particles can influence each other across vast distances without direct interaction hints at a universe where information might travel faster than light or even instantaneously. This challenges our classical notions of space and time, potentially leading to new theories about the fabric of reality itself. In practical terms, these ideas are already being explored in laboratories around the world. Researchers are working as we look back at our journey through the strange case of quantum entanglement. It's hard not to be left in a state of wonder. Quantum mechanics, like any other branch of science, is filled with mysteries that challenge our understanding of reality itself. Quantum entanglement, in particular, has been one of the most baffling and intriguing phenomena since its discovery. It defies common sense and challenges us to rethink how we perceive the world around us. The idea that particles can be connected over vast distances, no matter how far apart they are, is mind-bending. But as scientists continue their research, we see a blend of mystery and logic at play. On one hand, experiments have repeatedly shown that entangled pairs exhibit behavior that cannot be explained by classical physics alone. This has led to the development of new technologies like quantum cryptography and computing, which could revolutionize our world in ways yet unseen. On the other hand, there are still many questions left unanswered. How do these particles remain connected across space? Could it be a form of information transfer that we don't fully understand yet? Theories range from hidden variables to parallel universes, each offering its own explanation for this enigmatic phenomenon. The journey through quantum entanglement also reveals the beauty and complexity of scientific inquiry. It's not just about finding answers, it's about asking the right questions. Each experiment leads us deeper into a web of interconnected ideas that stretch far beyond our current understanding. For many, these mysteries fuel an insatiable curiosity. They ask, what are the limits of human knowledge? Can we ever truly know everything there is to know about this universe? Yet, for others, it might be more comforting to stick with what they can comprehend. The idea that particles could be entangled over vast distances challenges our sense of locality and causality in ways that feel unsettling. But perhaps the most intriguing aspect of quantum entanglement lies not just in its mysteries but also in how it forces not all mysteries have answers, but we keep searching. Subscribe to join the hunt.